Good morning, students. In the last class, we discussed about the experiment which is conducted by the Rutherford. That is, in that experiment, he gives the theory on the nucleus, and that is the existence of the nucleus and why the particles are scattered. That is, without any scattering, they passes through the stripe. Right. So those are the observations which did by the Rutherford. Right. So if we continue. So according to the Rutherford hypothesis, so the entire positive charges and the entire mass of the atom is concentrated to the small volume. So that he called the name as the nucleus. So nucleus is positively charged. So from the Rutherford hypothesis, so this is the nucleus of the atom. So this nucleus is contains the positive charges, right? So entire mass of the atom is concentrated into the small volume. So this volume only consists of the positive charges, and he named that one as the nucleus, and also the electron which is revolving around the nucleus, right? Like this. So this one is the electron. So electron is revolving around the nucleus. So whole this he called that one as the atom. So in the almost this atom is empty in space because electron is at a largest distance from the nucleus, right? So in the yesterday experiment, one alpha particle is approaching towards the nucleus, right? So this one is the alpha particle. So as the alpha particle approaches to the nucleus, the backward scattering takes place. The reason because the alpha particle is positively charged and nucleus is also positively charged. So for that reason, strong repulsive force will exert from this nucleus, right? So the size of the nucleus is much bigger than that of the alpha particle, right? So if we consider the nucleus, this one is from the gold foil, that is gold atom. So the nucleus size is 50 times bigger than that of the alpha particle. So for that reason, the backward scattering takes place. So as alpha particle is also positively charged and nucleus is also positively charged, the strong repulsive force is provided by the nucleus. So from the Coulomb's law, we can write the, that is, from Coulomb's law, we can write the repulsive force of the alpha particle to the nucleus, right? So here the charge of the alpha particle, so the charge of the alpha particle here we can take Q1, that is equals to 2E, right? So Q1 is the charge of the alpha particle, that is 2 times of the, that is alpha particle is nothing but the nucleus of the helium atom, right? So that one Q1 is equals to 2E. So similarly, if we take the nucleus, so nucleus is also positively charged. If here we can take Q2, that is equals to Z E, where Z is the atomic number of the nucleus, that is nucleus of the atom. So here we have taken this one as the gold atom, then the value of Z is 79, right? So here Q1 is equals to 2E and Q2 is equals to ZE. So from Coulomb's law we can, here is also the positive charge and here also the positive charge, hence the like charges will repulse each other, right? So where here Z is equals to 79 for gold atom, right? So Z is the atomic number of the atom. So here we have taken that one as the gold, right? So alpha particle is also positive charge. The nucleus of the gold atom, so nucleus is the entire positive charge is accumulated to the small volume. So here the nucleus is also positive charge. So Q 2 is equals to ZE. So from Coulomb's law, right? So from Coulomb's law. So from Coulomb's law of electrostatics. So as we studied in the first chapter, so we have the repulsive force because like charges will repel each other. Hence, we are getting the repulsive force. So repulsive force F is equals to 1 divided by 4 pi epsilon naught into Q1 Q2 divided by R square. So where R is the distance between the alpha particle and to that of the nucleus, right? So here, if we take the distance from here to here, then this distance is R. So R is the distance between the alpha particle and to that of the nucleus. So from Coulomb's law of electrostatics, F is equals to 1 divided by 4 pi epsilon naught into Q1 Q2 divided by R square. So where R is the distance between the alpha particle and to that of the nucleus, right? So here we have the Q1, that is 2E into Q2 we have ZE divided by where R is the distance, so it is R square, right? So this much of the force will exerted by the nucleus on the alpha particle. For this reason, because of the repulsive force, so the alpha particles takes the backward scattering when it approaches near to the nucleus, right? So this one is the repulsive force. This is from the Coulomb's law, right? The repulsive force, because the alpha particle and the nucleus both have the same charges, that is positive charges. For that reason only the repulsive force, the strong repulsive force is exerted by the nucleus on the alpha particle, right? So alpha particle as it approaches near to the nucleus, right? So this alpha particle approaches near the nucleus, so its magnitude and direction is continuously varying, because if you observe here 2E, that is the charge of the alpha particle, so this one is constant, and the charge of the nucleus present in the atom, so this one is also constant, and also 1 by 4 pi epsilon naught is also constant. So force is inversely dependent on the square of the distance between the alpha particle and to that of the nucleus. So force is inversely proportional to the distance as the alpha particle approaches near to the nucleus. That is because alpha particle is moving towards the nucleus. So as alpha particle approaching near to the nucleus, then its magnitude and the direction, that is force, because force is a vector quantity, its magnitude and also its direction continuously varying, because here we have taken R. So if the particle is here, then its distance reduces, right? So if we consider this one is 10 meter from here to here, so now this distance becomes 8 meter, right? So as it approaches, then its distance decreasing. As the distance varies, then the force magnitude also varies, and along with that the direction also varies, because the force is a vector quantity, right? So as the alpha particle approaches near to the nucleus, so its magnitude and direction is continuously varying, right? Because it's a moving particle. For that reason the distance varies each time, then its magnitude and direction also changes, right? So as the alpha particle is vector, so its direction is always along the line joining, so its direction is always along the line joining the alpha particle unto that of the nucleus, right? So in this direction, if this one is the repulsive force, so this becomes F. So the direction of the alpha particle is always along the line joining the alpha particle and the nucleus, along the straight line, right? So this one is the direction of the repulsive force, right? So here we have the force F is equals to 1 by 4 pi epsilon naught into 2e Z e divided by r square, where Z is the atomic number of the atom. As the nucleus is very large compared to that of the alpha particle, that is, it's as heavier than the alpha particle. So for that reason, considering nucleus as stationary, as alpha particle approaches near to the nucleus, then strong repulsive force is exerted by the nucleus onto that of the alpha particle. So that repulsive force is given from the Coulomb's law of electrostatics, that is F is equals to 1 by 4 pi epsilon naught 2e into Z e divided by r square. So the direction of the repulsive force is always along the line joining the alpha particle unto that of the nucleus of the atom, right? So as the force is a vector quantity, then the each time, that is the magnitude and direction of the alpha particle, that is varies continuously, right? Because it depends only on the distance between the alpha particle and the nucleus, right? So next, this is the repulsive force, right? Next, as the alpha particle approaches towards the nucleus, here we are getting the repulsive force. That means this nucleus is opposing the alpha particle to approach the nucleus. That means it traveling with a velocity v. As it moves towards the nucleus, its velocity goes on decreasing. That means its kinetic energy goes on decreasing as it moves near to the nucleus. So as the kinetic energy decreases, then automatically the potential energy of the alpha particle increases, right? So as the alpha particle approaches near to the nucleus, its velocity goes on decreasing because the opposition of the force which is exerted by the nucleus. For that reason, its kinetic energy decreases, right? So as kinetic energy decreases, then automatically the potential energy will increase for a particular distance. For example, if this particle here somewhere here, so this is the alpha particle. So as this alpha particle is moving in this direction, that is towards the nucleus, then at a particular distance from nucleus to alpha particle, we consider that one as R naught. So here the entire kinetic energy of the alpha particle is converted into its potential energy for a particular distance. As it approaches near to the nucleus, the repulsive force exerted by the nucleus will act on this alpha particle. For that reason, its velocity decreases. So as velocity decreases, its kinetic energy decreases. So kinetic energy decreasing means its potential energy is increasing. So for a particular position from the nucleus, so this one is the alpha particle. So here the entire kinetic energy is converted into its potential energy. That is K is equals to U for a distance R naught. So if the alpha particle is at a distance R naught, then its kinetic energy is almost converted into its potential energy. So this distance we call that one as the distance of closest approach. So after this, again it comes backwards, right? So this distance R naught we call as distance of closest approach. Distance of closest approach. So that is R naught, right? So understand this one. Alpha particle is, that is the alpha particle which are coming out from the radioactive source is moving towards the atom. So this is the gold atom considered, means this one is the nucleus. As it approaches towards the nucleus, a strong repulsive force is produced by the nucleus because it is heavier than that of the alpha particle. Because of the repulsion, as the alpha particle approaches towards the nucleus, its velocity decreases. As its velocity decreases means its kinetic energy decreases. As the kinetic energy decreases, automatically the potential energy of the alpha particle increases. For a particular distance from the nucleus, the entire kinetic energy of the alpha particle is converted into the potential energy. So that distance we call as distance of the closest approach, right? So the condition is kinetic energy is equals to potential energy. So here we know the kinetic energy is half mv square. So where v is the velocity of the alpha particle, so that is equals to the potential energy. So here we have the charge q and here we have the charge of the nucleus, that is charge of the alpha particle and the charge of the nucleus. So from that is, as we already studied in the electrostatic, that is potential energy u is equals to 1 by 4 pi epsilon naught q1 q2 divided by r, that is the distance between the alpha particle and to that of the nucleus. That is, as it approaches near where the entire kinetic energy is converted into its potential energy. So from that we can write 1 divided by 4 pi epsilon naught into q1, that is 2e into ze divided by r naught. So that is the potential energy, where r naught is the closest distance, that is distance of the closest approach. So at this position, the entire kinetic energy is converted into its potential energy. So here we can't write the distance r, because here we are here at this distance, the entire kinetic energy converted into potential energy. For that reason, so this one we can take as r naught, right? So from this we need r naught, that is the distance of closest approach. So if we rearrange r naught, that is equals to 1 divided by 4 pi epsilon naught 2e into ze. So these two moves to the RHS, means it goes to the numerator, into 2 divided by m v square goes to the denominator, right? So finally we can write r naught is equals to, so that is 4z e square divided by 4 pi epsilon naught m v square. So this is the distance of the closest approach where entire kinetic energy is converted into its potential energy. So this is the repulsive force and this one is the distance of the closest approach, right? So understand this one. So r naught is the distance of the closest approach, right? So next, so this is about the repulsive force. This is from the Coulomb's law of electrostatic. So this is also from the Coulomb's law of electrostatic. So this one is the potential energy of the two charges. The formula is 1 by 4 pi epsilon naught q1 q2 divided by r. So here q1 is 2e and q2 is ze, where z is the atomic number of the atom. So if we consider this one as the gold, then z value is equals to 79, right? So this is about the repulsive force and also the radius of the closest approach, sorry, the distance of the closest approach, right? So next, So next is alpha particle trajectory. So next topic is alpha particle trajectory. So what is trajectory? So trajectory is the path followed by a particle in a free space. So that one we termed as the trajectory. So as already once studied in class 11, that is in motion in a plane, that is as we throw a ball or as the particle moves in a plane, then the path followed by that particle is the trajectory of the projectile. That one we is represented as the, so this one is the trajectory of the path followed by the particle. So as if this one is the ground, so then it has traveled with its velocity u, then this projectile trajectory is parabola, right? So as already studied in the class level. So this path followed by a particle in free space, then that named as the, that name is given as the trajectory. So in a simple word, we call that one as the trajectory. That is path followed by the particle in free space. So that one we call as the trajectory. So here we are studying the path followed by the alpha particle. So in which path the alpha particle is traveling, right? So here the alpha particle trajectory, right? So trajectory means path followed by a particle in free space. So that one named as the trajectory. So here we are studying the alpha particle trajectory. So alpha particle's trajectory is depend on the impact parameter of the collision, right? So the alpha particle trajectory depends on the impact parameter of the collision. That is the trajectory of the alpha particle depends on the impact parameter of the collision. So here the path which followed by the alpha particle depend on the impact parameter. So here what is impact parameter? So the path followed by this particle is directly, which is depends on this impact parameter, right? So based on this impact parameter, we can say how the particle, that is alpha particle, is traveling. That is how the alpha particle is moving in free space. So here the trajectory of the alpha particle is mainly depends on the impact parameter of the collision, that is collision between the alpha particle and to that of the nucleus, as we studied in the last class, that is scattering, right? So here what is impact parameter? So the impact parameter is the distance, perpendicular distance of the alpha particle initial velocity to that of the center of the nucleus. So that is called the impact parameter. So impact parameter is the perpendicular distance between the initial velocity of the alpha particle and to that of the center of, that is from the center of the nucleus. So that distance we call as the impact parameter. So on that distance the trajectory depends of the alpha particle, right? So what is impact parameter? So impact parameter is the perpendicular distance of the initial velocity of the alpha particle from the center of the nucleus of the atom. So that distance we call as the impact parameter, right? The impact parameter is the perpendicular distance of the initial velocity vector of the alpha particle from the center of the nucleus of atom. Right, so this is the definition of the impact parameter, right? So what the definition says here, so this one is the nucleus. So nucleus is positively charged and the entire mass is accumulated in this volume, right? So this one is the nucleus, right? So this is the axis of the nucleus. So this one is the axis of the nucleus, right? So here what it says means the perpendicular distance of the initial velocity vector of the alpha particle. That is, alpha particle is moving towards the nucleus, right? So here somewhere here is the alpha. This one is the alpha particle, right? So this alpha particle, so it has started with initial means it has initial velocity, right? So the path followed by this alpha particle, right? So like this, right? So here where we'll get the impact parameter. So this one is the initial velocity of the alpha particle, and here the center of the nucleus means here we have the axis, right? So this distance, is called the impact parameter. This one is the perpendicular distance from the center of the nucleus to the initial velocity vector, right? So during the collision, right? So this one is the impact parameter, right? So this distance, the perpendicular distance of the initial velocity vector of the alpha particle from the center of the nucleus. So here we have the center means here we have the axis. So this distance we call as the impact parameter. So impact parameter is denoted by the symbol B, right? So this distance can be represented by B. That is the perpendicular distance of the initial velocity vector of the alpha particle from the center of the nucleus of the atom. So that distance we call as the impact parameter. So on this parameter B, so B decides how the path will be moved by the alpha particle. So the trajectory of the alpha particle depends on the term, that is impact parameter, that is B, right? So this B is the perpendicular distance of the initial velocity vector from the center of the nucleus of the atom, right? So from this we can observe the path followed by the alpha particle. So understand this one. So alpha particle is here. So the distance, perpendicular distance from center of the nucleus to the initial velocity vector of the alpha particle, then that distance we call as the impact parameter, and it is denoted by B, right? So here as it approaches towards the nucleus, then it gets scattered, that is during collision. So this one is important. So as already studied in class 11, collision, different types of collision, that is oblique collision, head-on collision, right? So here if what happens, the alpha particle is collide head-on with the nucleus, right? So if we have the number of, that is beam of alpha particles, right? So here if we consider one more, that is beam of alpha particles, I will represent in different colors. So impact parameter is denoted by the letter B, right? So this is the another alpha particle, right? So next, here another alpha particle, considering one more alpha particle. If I consider means, right? So this one is here. If I consider this black one, this is the theta, that is scattering angle. Right. So here we have a beam of alpha particle. Here 1, 2, 3, 4. So here we have a beam of alpha particle. So after it approaches near to the nucleus, it will travel in different directions. That is different possible direction. That is it scatters in different directions. So if you observe here, so it is backward scattering, and the black one is scattered with an angle theta, and here the green one is scattered perpendicular to the axis of the nucleus, and the blue one is making an angle theta, right? So these are the beam of the alpha particle, right? So here the B values varies, right? So here if I observe for this red one, the B, it one is B1, for black already it is B, this one has B2, and for green it is B3, and for it is blue it is B4, right? So that is the distance from this axis for the different alpha particle is varies. That is here we have for red B1, for here black we have B2, for green color we have B3, and for blue color we have B4. So these are the impact parameters. That is the distance B varies. That is the perpendicular distance varies for the each alpha particle. For that reason only trace different path, right? So all the alpha particle will not follow the same path because the V value is varying. For that reason only the scattered alpha particle will follow the different paths, right? So here from this we can say that the alpha particle initial velocity vector is directly depend on the factor, that is the impact parameter, right? So here when we will get the maximum and when will we get the minimum, right? So consider this one as nucleus. This is the axis, right? So when or if an alpha particle makes an head-on collision, right? So exactly the alpha particle is on the axis of the, so this one is the alpha particle. So this is along the axis of the nucleus, right? So as alpha particle makes head-on collision with the nucleus. So if we observe here, we need to measure the perpendicular distance of the alpha particle initial velocity with that of the center, that is axis of the nucleus. So if I observe means both are in a same line, that means that the impact parameter is minimum, that means the value b is 0, right? So here impact parameter, so that is represented by b, right? So here in the last, here I will explain, this is the nucleus means this is the trajectory of the alpha particle, right? So this distance is the impact parameter b, that is the perpendicular distance from of the initial velocity vector of the alpha particle from the center of the nucleus of the atom, right? So if observe here, so here is the alpha particle and it is making the head-on collision with the nucleus. That means it is along the axis of the nucleus. That means the value of the b is minimum. That means the b minimum. That is during head-on collision. Right? So during head-on collision, the impact parameter is minimum. Then it retraces back the same path. That is like this. That is the angle theta is scattered, where scattering angle theta is how much here? So this is in the direction means 0 degree, so that is opposite direction, that is here. After scattering it goes back means 180 degree, that is pi. So approximately equals to pi, that is the scattering angle theta is equals to pi, right? So when during head-on collision the impact parameter is minimum, that means b value is 0, then the scattering angle theta is almost equals to pi, right? So understand this one, because the alpha particle for the head-on collision it is lies along the axis of the nucleus, right? So here there will be no perpendicular distance between the the alpha particle and to that of the nucleus, that is there will be no this distance, because these two lie in the same plane, hence the b value is 0. So if the b value is 0 means the b value is minimum, that is impact parameter is minimum, then the scattering angle theta is equals to pi, that is it scattered back with an angle 180 degree, where theta is the scattering angle, right? So this is for the minimum, right? So next, in the next case, so this is the nucleus of the atom and this is the center of the nucleus, that is axis which is drawn along the center of the nucleus. Now we have studied about the minimum. Now for maximum, if I consider the alpha particle is here, so this distance is the distance parameter is more, that is the b is maximum. When b is maximum, right, so the alpha particle will go straight without any scattering, that is for maximum impact parameter there will be no scattering of the alpha particle. So here the scattering angle theta is almost equals to 0. There will be no scattering, right? So in the experiment also we explained, so here is the nucleus and the electron which is revolving around the nucleus is of the order 10,000 times that of the nucleus. So almost 10,000 times means somewhere here. So up to this space the atom is almost empty. So the alpha particle which are passing away from the nucleus will go straight without any deviation, right? Hence we are getting maximum low angle scattering. So in the last experiment observation we did, the first observation is the low angle scattering. That is the reason, because if the impact parameter is maximum, then there will be no scattering of the alpha particle. Right? So these are the two cases. So one, when the angle is minimum, that is during head-on collision, the alpha particle is along the axis of the nucleus, then its B value is minimum, then the angle of scattering is, that is 180 degree. So for the maximum distance, perpendicular distance from the nucleus to the alpha particle, that is B is, if I observe, so this one is the largest distance, the impact parameter is maximum. For that reason, here there will be no scattering. So in between, somewhere here, if the alpha particle is makes collide with this nucleus, then it deviates like this, makes with an angle 90 degree. Right? So if I observe here, so this one is the impact parameter B. So from this we say that the trajectory of the path followed by the alpha particle directly depends on B. Right? So if I consider one more here, then this one is the scattering. So this is during collision. So this one is the after collision. So if I find, so this is the angle theta, that is after scattering. Here angle theta is 180 degree and here angle theta is 0 degree. So this is for the minimum impact parameter and here this one is for the maximum impact parameter. So this is about the alpha particle trajectory, right? So in the next class we will discuss about the radius of the, that is electron orbit. So until now we studied about the part of the nucleus, that is nucleus, its trajectory of the alpha particle and the repulsive force of the nucleus and the minimum distance of the least approach of the alpha particles towards the nucleus, right? So this is about the alpha particle trajectory. In the next class, we will continue the electron orbit. Thank you.